In this video, we're going to look at Stokes Theorem. We're going to use Stokes Theorem to evaluate a line integral. We're going to use Stokes Theorem to calculate a surface integral. And we're also going to use it to calculate curl. Stokes Theorem is to surface integrals, kind of like Green's theorem is to line integrals. Stokes Theorem says we can calculate the flux of the curl f across the surface S by knowing the information only about the values of f along the boundary of my surface S. Conversely, we can calculate the line integral of a vector field f along the boundary of a surface S by translating to a double integral of the curl f over S. Let S be an orientated smooth surface with a normal vector n. Furthermore, suppose the boundary of S is a simply closed curve C. The orientation of S induces the positive orientation of C if you walk around the positive direction of C with your head pointing in the direction of N. The surface is always on your left. This is the definition that we need so we can use Stokes' theorem. Stokes' theorem says, let S be a piecewise smooth orientation with a boundary that is simply a closed curve C with a positive orientation. If F is a vector field with component functions that have continuous partial derivatives on an open region containing the surface S, then we can find the integral over the curve of f dotted with dr, this is the dot product, which is equal to the double integral over the surface of the curl of f with a dot product ds. So this is the orientation that we were talking about. Notice our orientation to be positive is going, if I were to look down on the xy plane, we are going counterclockwise. So this is y and that's x. So we want to think of this as a counterclockwise rotation. And the reason you want to do that is when you think about, if you're an engineering student, if you put your hand right here, this is your hand. There's your hand. Here's your thumb. If you were to wrap your fingers around the y or the z axis, your thumb pointing upward would be positive, your thumb pointing downward would be negative. It's a right-hand rule. Again, Stokes' theorem is great because it relates the flux integral over the surface to a line integral around the boundary of the surface. And we have to pay attention to the orientation. It's true for the case of a function with a domain that is simply connected region of a finite area. If f is conservative, the curl, if my vector field is conservative, then the curl of f is 0. So the curl of the double integral over the surface S of my vector field f dotted with a ds will equal 0. Since the boundary of S is a closed curve, then the integration across the curve with f, my vector field dotted with a dr, is also equal to 0. One of the consequences of Stokes' theorems is that if S prime is any other smooth surface with the same boundary C and the same orientation as S, then the curl, the double integration over the surface of the curl of f dotted with ds is equal to the integral over the curve of my vector field f dotted with dr, and it'll equal 0 because Stokes' theorem says the surface integral depends on the line integral around the boundary only. Similarly, suppose that S and S prime are the surfaces of the same boundary and the same orientation. Suppose that G is a three-dimensional vector field that can be written as the curl of another vector field f, so that like f is the potential field of G, then the double integral of the surface S of G dotted with ds is equal to the double integral of the surface S, the curl, the vector field f dotted with a ds, is equal to the single integral across the curve f dotted with dr, which gives us this. Therefore, the flux integral of G does not depend on the surface, only the boundary of the surface, and flux integrals of vector fields can be written as the curl of a vector field are surface independent in the same way that line integrals of vector fields can be written as a gradient of a scalar function that are path independent. We want to use Stokes' theorem to evaluate the curl of my f dotted with n ds. Well, one of the things that we end up with all of this is we think about this in Green's theorem. Remember that the double integral over the surface of the curl of f dotted with n and ds is the same thing as the curl, the single or the double integral over the curl of the surface S, the curl of f dotted with ds, which is also the single integral of the over the surface C, or excuse me, over the line integral C of f dotted with dr. So what they're really asking me to do then is basically do this here. So the first thing we're going to want to do then is to find the flux of the curl of f dotted with n over the given surface that's given to us. So we want to consider this cube. This cube is from 0 to 1 in the x, 0 to 1 in the y, and 0 to 1 in the z. So we have a cube that looks something like this. My poorly drawn cube will look like this. I'll have 1 in the x, 1 in the y, 1 in the z. Here's z, y, and x. It's going to have some box-like structure like this. Okay, and of course each one of these corners, this corner would be 0, 1, 1. This corner would be 0, 1, 0. This corner would be 1, 1, 0. And you get the gist of it. What we know is the integration over the surface area S of the gradient crossed with F, the vector field F, dotted with ds, is going to be equal to the circulation around the curve C of f dotted with dr. So that means that using Stokes theorem, we're just going to look at the curve on the xy plane. So looking at the xy plane, I'm going to have this point which is 1, 0, have this point which is 1, 1, and this point which is 0, 1, and my final point which is 0, 0. Now remember, we have to go in the counterclockwise position, so it's going to look something like this. Now, if we break up each one of these individual curves, call this C1, C1 would have t for x and 0 for y, and for t being from 0 to 1. C sub 2 would be 1 for the x and t for the y. C sub 3 would be, it would be 1 minus t for the x and 1 for the y. And C sub 3 would be 0 for the x and t minus 1 for the y. As I walk around the outside of this, now remember, when I do the integration, and I can integrate this over each one of the individual curves, that we've got to do that replacement of my C of t, or R of t, if you will. So R of t is going to be equal to t comma 0. When I do f of R of t, then for this first one, I'm going to get, since y is 0, I'm going to get 0, and since z is 0, that's going to be 0. So I'm not going to get anything with my first curve right here. Okay. If I look at my second curve, then my R of t here will be 1 comma t. That's not too bad, right? So then my f of R of t, well, this is going to give me t and then 0. But my R prime of t, which is what I'm going to need for the integration, is going to be 0 comma 1. So when I do this integration, from 0 to 1 of f of r of t dotted with r prime of t dt, this is going to go to 0. Just like this one from 0 to 1 of f of r of t dotted with r prime of t, this also is going to go to 0. Okay, so that's not helpful. Let's look at my third one. So let's look at c sub 3. C sub 3, I had 1 minus t, comma 1. So my r of t is going to be 1 minus t, comma 1. That's looking promising. R prime of t is going to be, negative t, comma 0. That's not looking too bad. And then my f of r of t, and that's going to be 1 minus t and 0. Oh, well, that's not too bad. So then my integration for this one from 0 to 1 is going to be 1 minus t, comma 0, dotted with negative t, 0. Oh, excuse me, that should be negative 1. What was I thinking? That's negative 1. Negative 1. That's negative 1. Let me erase that, make that negative 1. And this is going to give me the integration from 0 to 1 of negative 1 plus t dt, which is going to give me negative t plus t squared over 2, evaluated from 0 to 1. So negative 1 plus 1/2 gives me negative 1/2. So that's I got a first one right here. I have my first answer. I'm pretty excited. And it is not equal to 0. So this is negative 1/2. Now let's take a look at my c sub 4. This should be c sub 4. My c sub 4 is the vector defined by 0, 1 minus t. This should be 1 minus t. Let me change that to 1 minus t. This should be 1 minus t. 1 minus t. And this should be 1 minus t. And then, so my vector, r of t, is going to be 0, 1 minus t. Then my f of r of t, f of r of t, not prime, just t, is going to be, well, since my x is 0, it's going to be 0, comma 0. So I don't get anything from this one either. This integration from 0 to 1 of f of r of t, r prime of t dt, also goes to 0. So my final answer is just this. And you're thinking, but wait a minute, going from 0 to 1 isn't the correct orientation, because I should be going backwards. Well, the way I adjusted for it is I did 1 minus t. I could have easily have said that this would have been t here. I could have just said this is t. And then when I would have done the integration, it would have been from 1 to 0. So that could have fixed the orientation, but I did 1 minus t. That also fixed the orientation. So I just want to make sure that you realize why I did 1 minus t, and it still worked out for 0 to 1 versus it should have been 1 to 0 because the orientation, but because I did 1 minus t, I got my orientation that way. Okay, now let's take a look at the second example here. For this one, what we're going to use is Stokes Theorem, which is the integration along the surface S of the curl of f dotted with the normal vector and then ds is equal to the integration along the curve f dotted with dr. So I need to parameterize. I have this intersection of this sphere and with the plane z equals 0. So that means I'm working at the top part of my hemisphere. I have a hemisphere, basically. So a good choice for my r of t would be wherever I see x, I'm going to replace it with r cosine. So I'm going to consider that r squared. So it would be r cosine, which is 2 cosine of theta. And then I have 2 sine of theta. And then because I am intersecting with the plane z equals 0, we have 0. So in other words, I really have a circle, which is x squared plus y squared is equal to 4. I really have a circle on the xy plane because z is equal to 0. So then r prime of t is going to give me negative 2 sine of theta, 2 cosine of theta, and 0. And I should mention that since we're looking on the xy plane as a circle, theta is going to run between 0 and pi, 2 pi. Now I could use t here instead of theta, but I just kind of like theta. So then my f of r of t is going to be equal to, wherever I see y, I'm going to replace with 2 cosine, so I'm going to get 8. The sine of theta, and then I have z, which is 0, and then I have 2y. Oh, that must be, I must have 2 x's. I must have 2 y's here. One of these must be an x in my f function. So let me erase this. And I'm going to go out and check, because notice I've got y and y. I believe I should have an x and a y, so give me just a moment. Nope, I wrote that down correctly. It's 4yi plus z and 2yk. So then my f of r of t is going to be equal to 4 times my y, so that's going to give me 8 sine of theta. My z is 0, and then I have 2y, so that's going to give me 4 the sine of theta. Okay, so now I'm ready to set up the integration. So this c from f dotted with a dr is going to be the integration of c of f of r of t dotted with r of t dt, which is going to be equal to 2, not 2, sorry about that, it's going to be 8 sine of theta, 0, and 4 sine of theta from 0 to 2 pi, dotted with negative 2 sine theta, 2 cosine theta, and 0, d theta. Now when I do this dot product, I'm only going to be left with 0 to 2 pi of negative 16, the sine squared theta, d theta. Because when I do the dot product, these two are going to produce 0, and these two are going to produce 0. So then I just look this up in the integration tables, and I get negative 16 from 0 to 2 pi. I can do a power reduction formula if I'm inclined, or I can just go ahead and look these up in the tables for the sine squared of theta, d theta, and I'll let you finish that one off. Now let's take a look at c. My making sure I've got everything right on this one. S is the half sphere, where x, now this is the important thing, is that this is x. So that means this is where my mistake was. That should be y squared. So 1 minus y squared minus z squared. Again, I'm going to be using the Stokes theorem, so the integration along the surface S of the curl of f dotted, or excuse me, it should be an in there, dotted with the vector, the normal vector, ds is equal to the integration along the curve of f dotted with dr. So I have a half sphere and I am orientated out toward the positive x-axis, and now notice that x is equal to this function. So what that means then, and I'm looking at this as, I really am looking at the plane of x equals 0. So I'm going to be looking between this and this. This tells me that I'm looking at the plane x is equal to 0 by the way that I am orientated. So then what I really have is the equation 0 is equal to the square root of 1 minus y squared minus z squared, which gives me y squared plus z squared is equal to 0. So, excuse me, is equal to 1. So basically, I'm on the yz plane with a circle with a radius of 1, and it choose however you want. Now, traditionally, cosine would go with sine, sine would go with y, and cosine would go with x. So we can stay with that and use the z as the cosine. But we've got this is y and this is z is how I'm going to do this. So my r of theta will be equal to, in this case, I have the 0 in the x, and I'm going to use y and cosine together because the way I've orientated my axes. So it'll be the cosine of theta, and then I'm going to put z with sine, so that's the sine of theta. You can switch those if you want, and if you do that, that's fine. You'll make this y and this z. It's totally fine. Just make sure you're consistent when you do the replacement. R prime of theta is going to give us 0, negative sine theta, cosine theta. And then my f of r of theta is going to be, and this should be theta up here. That should be theta because I'm using theta. And this should be theta, theta, d theta, just for notation purposes. Is going to be equal to, I have e raised to the xy, so that's e raised to the 0. The cosine of the cosine, or excuse me, the cosine of the sine of theta, comma, and then I have 0 times z, so that's 0. And then the last one is 0. So now I'm ready to do the integration. My theta, again, is going to run between 0 and 2 pi. So I'm going to have from 0 to 2 pi. So by Stokes theorem, the curl of f dot dr is equal to, and I'm using theta. So then this is going to be equal to the dot product of 0, negative sine theta, cosine theta, cosine of the sine of theta, 0 and 0, d theta, which is going to go from 0 to 2 pi. Oh, this is nice. This gives me 0, this gives me 0, and this gives me 0. So I had a moment like, oh my gosh, that's not going to be very nice, but really, it's really quite nice. So I was thinking, oh, I have to integrate the cosine of the sine of theta, but I didn't. It equals 0. Let's take a look at the next example. We use the surface integral in Stokes' theorem to calculate the circulation of the field F, where F is defined as x squared y cubed I plus j plus z k squared around C, which is the intersection of the cylinder of x squared plus y squared is equal to 4, and the hemisphere of x squared plus y squared plus c squared is equal to 16, and z is greater than or equal to 0, we are orientated counterclockwise when viewed from above. Now we know from Stokes' theorem that the integration along the curve of f dotted with dr is the double integration along the surface of the curl of f dotted with n ds. And these are vectors or vector fields. Okay. So first thing is that I have this hemisphere here, and I have this cylinder x squared plus y squared is equal to 4. And I'm going to need to parameterize them. And so I'm going to do it with the theta and phi, because I'm in the XYZ, that's a cylindrical, or that's a spherical. So it's going to be easier to do the parameterization of the hemisphere first. So I'm going to have R of theta and phi, which is going to be equal to my radius, or my rho, which is 4. So that's 4. And then it's going to be the cosine of theta, the sine of phi, comma, 4, the sine of phi, the cosine, the sine, I'll do it consistently, the sine of theta, the sine of phi, that's a phi, not a 4, and then 4, the cosine of phi. So that's my r theta vector. Now I have to figure out what's going on with those. So my theta, obviously, because we're doing a circle on the xy plane, this would be their theta. Theta is going to go between 0 and 2 pi. I have to figure out what phi is doing. Well, I have to, looking at down my xy plane. So this is z, and this would be y. I have this hemisphere right here, and I have it crossing this cylinder. So I have to figure out where those two pieces match so I can figure out what phi is. That's going to be my phi. That's not 4, that's a phi. So I have to figure out where phi crosses. Now, I know that at the most this thing is going to be 4. And the location of where this intersects is, I know that x squared plus y squared is equal to 4. So I can replace that here. And so I have 4 plus z squared is equal to 16. And z squared is equal to 12. Z is going to be equal to square root of 12 plus and minus, which is 2 root 3 plus or minus. Now, my 4 cosine of phi is going to run between the absolute value of this is going to run between, or is going to be less than 2 the square root of 3, because that's going to tell me where I'm going to cross. So in other words, I can divide both sides by 4. So the cosine of phi, the absolute value, has to be less than square root of 3 over 2. And because phi must be in quadrants 1 and 2, the cosine of phi must be equal to the square root of 3 over 2. So then phi, looking on my unit circle, must be pi over 6. So now I know that phi runs between 0 and pi over 6. Okay, so that was a lot of work to figure out what phi is going to run between. Now I'm ready to do my tangential vectors. So I have my tangential vectors u, or excuse not u, but the theta. So my tangential vector of my r with respect to theta is going to be negative 4 the sine of theta, the sine of phi. And then for the cosine of theta, the sine of phi, and 0. My tangential vector with respect to phi is going to be for the cosine of theta, the cosine of phi. For the sine of theta, the cosine of phi. And then negative 4, the sine of phi. And that's it. Okay. So once I've done that, because I need the curl, I'm going to find my cross product for my curl. So then my cross product in the I direction, my first row is going to be my u tangential, or not my u, my theta tangential vector, which is going to be negative 4, the sine of theta, the sine of phi. In the j direction, it's going to be 4, this cosine of theta, the sine of phi. In the k direction, I have 0. My next row is going to be 4, the cosine of theta, the cosine of phi. For the sine of theta, the cosine of phi, and minus 4, the sine of phi. Okay, in the I direction, I'm going to have negative 16, the cosine of theta, the sine squared of phi in the I direction, and then minus, I'm going to have in the j direction, I'm going to have a positive 16, the sine of theta, the sine squared of phi in the j direction. And then in the k direction, so plus, in the k direction, I'm going to get negative 16, the sine squared of theta, the sine of phi, the cosine of phi, minus 16, cosine squared, the cosine squared of theta, the sine of phi, the cosine of phi in the k direction. Now, of these two, I can factor out a negative 16, the sine of phi, the cosine of phi, leaving me sine squared of theta plus cosine squared of theta, which we know happens to be 1. So then what I have is negative 16, the cosine of theta, the sine squared of phi, negative 16, the sine of theta, the sine squared of phi, negative 16, the sine of phi, the cosine of phi. And there is my cross product. So we're going counterclockwise. So we want to consider the inward normal surface would be, the inward normal surface would then be the opposite. So 16, the cosine of theta, the sine squared of phi, 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 pho, phum, phi, and then 16, the sine of theta, the sine, there's a terrible S, don't know what's happening there, the sine squared of phi, and then the 16, the sine of phi, the cosine of phi. All right, so that's my normal vector. Now what I have to do is find my curl of f, which we know is equal to, in the I, the j, and the k direction, the partial with respect to x in the first and the second row, the partial with respect to y in the next position, and the partial with respect to z. And for my f function, I have x squared y cubed, so x squared y cubed. I have 1 and z, so 1 and z. This gives me, when I totally get done, negative 3 x squared y squared in the k direction. And that's it, because everything else is going to go to 0. So now, with the replacements, negative 3 x squared y squared in the k direction, with the replacement is negative 3. Now remember, my x, going back to my r theta, is going to be 4 the cosine of theta, the sine of phi, the quantity squared, and my y is going to be 4 the sine of theta, the sine of phi, the quantity squared, in the k direction. That should be a hat, not a bar. Give me a moment to change that. It's a hat, not a bar. So k, hat, so that's my vector, which is going to be 0, 0. And I'm going to square 4 twice, so that's 16 times negative 3, which gives me, let me go grab my calculator, negative 768. I'm going to end up with a cosine squared theta, a sine squared theta, and a sine to the 4th of phi as my curl of f. Now, I'm finally ready to do the integration. So my integration on my surface of the curl of f dotted with n ds is equal to, I'm going to integrate with respect to theta last, so from 0 to 2 pi, from 0 to pi over 6, that's going to be my phi, of 0, 0, negative 768 cosine squared theta, sine squared theta, sine to the 4th phi, dotted with my, I did my n first, or I did my curl first. My n, which is 16, the cosine of theta, the sine squared of phi, 16 the sine theta, the sine squared of phi, and 16 the sine of phi, the cosine of phi, d phi, d theta, which gives me from 0 to 2 pi, from 0 to pi over 6. Well, most of it cancels out, so that's kind of nice. I'm going to have negative 768 and times 16, which gives me negative 12,288 of. I'm going to have the cosine squared theta, the sine squared theta, the sine raised to the 5th of phi, the cosine of phi, d theta, d phi, d theta, d phi, d theta. All right. Now, the thing is that we can treat the thetas as constants, and so we can rewrite this as from 0 to 2 pi of. Well, actually, you know what? Let me pull out the negative 12,288. From 0 to 2 pi of the cosine squared theta, the sine squared of theta, multiplied by the integration from 0 to pi over 6 of the sine to the 5th of phi, the cosine of phi, d phi, and of course I need to put in my d theta. Now, this we can do a U sub if we wanted to. We could say let U equal the sine of phi, and du is equal to the cosine of phi d phi. It's totally fine to do that. If you do that, make sure you change your limits of integration. If you don't change the limits of integration, that's okay. We know that this part ends up becoming the sine raised to the 6th of phi divided by 6, evaluated from 0 to pi over 6. Now this other portion, I have the sine squared and the cosine squared. We can just use a table of integration. We could use a power reduction. We can do a replacement for cosine squared. Cosine squared is 1 minus sine squared. So there's a bunch of ways of approaching that, and then you're going to do that integration. Your final answer, by the way, when you get done, however you end up doing the integration, is going to be negative 8 pi. So even though this was interesting, potentially you could lose stuff along the way, the answer's pretty nice. Okay, go back and do some more. So I need to erase all of this, because I'm going to need this space over and over and over again. And these are long. I'm not going to lie, these are long, very, very long. It takes a long time to do that one. So let me erase all of that. Okay, let's look at my next example here. I don't know why I lose my lock. It just drives me batty. You know what I was going to say. I'm not going to say it. Okay. Here we go. Use Stokes' theorem to evaluate the circulation of the dot product of the field F with ds, where F is defined as x squared, x, y, z, x, y, z is equal to y in the I, z in the j, and x in the k, with C is a triangle with vertices of 0, 0, 2, 0, 0, 0, negative 2, 2, orientated counterclockwise when viewed from above. Well, the first thing we're going to want to do is figure out the plane that is being formed by these vertices. So I have 0, 0, I have 2, 0, 0, and then I have 0, negative 2, and 2, so something like this. So I'm gonna have this triangle shape here, and it's going to form a plane. So I'm going to just start labeling these. I'm going to call this P, I'm going to call this Q, and I'm going to call this R. So the vector from P to Q is equal to 2, 0, 0. That's nice. The vector from P to R is the vector 0, negative 2, 2. If I do the cross product of PQ with PR, I'm going to get, in the IJK, I'm going to get 2, 0, 0, 0, negative 2, and 2. This is going to give me 0 in the I, plus 4 in the J, and minus 4 in the K. Now we know from previous chapters and Calculus 2 that we end up now with the normal vector to the plane. So the plane can be described as my 0 and then x minus my 0 plus 4 and then y minus my 0, because I'm going to choose any point. I'm 0, 0 being the best point, and then negative 4 and then z minus 0 is equal to 0. So then what I have is 4y minus 4z is equal to 0, and this is going to describe the plane. So that's the plane that it's on. So now I'm going to find the curl of f, because I know that this is going to be the surface area on the curl of f dotted with a ds, which is going to give me the the integration along the curve of f dotted with a ds. So I'm going to find my curl of f, which is going to be the I, the j, and the k, the partial with respect to x, the partial with respect to y, the partial with respect to z of y, z, and x. And I end up getting negative I minus j minus k. All right. Also, this should be the normal ds. Okay. So now we're going to parameterize this surface. So that's my triangle. So my triangle is 4y is equal to 4z, which tells me that y is equal to z. So if y is equal to z, then I'm going to parameterize this as r of x and y. So I have the vector x, y, and y. Now, the reason that I have to have x, y, and y is because I don't have any relationship between y, x, and z. So I have y and z, but I don't have x and z. So my surface will be x. X is going to change along here or along any of the other ones. So it's going to be x, y, y, because this is going to be in terms of, z is going to be in terms of y. Now I have to find my tangentials in each direction. So I'm going to do my tangential with respect to x. And this is going to give me 1, 0, 0. I'm going to do my tangential in terms of y. These are all vectors. Is going to be 0, 1, 1. Now I'm going to do the cross product of t crossed with t sub y. So I, j, and k of 1, 0, 0, 0, 1, 1. And when I do that, I'm going to get the vector 0, 1, 1. And you notice I haven't done anything about, when I talked about my parameterization, the limits on the y and the x and all of that. That's okay. Let's see what happens if we just are ready to start doing the integration. Now my integration across my surface area of the curl of f dotted with the normal and ds is going to be equal to, along the surface S, my curl, I ended up with -1, -1, and -1. My n is 0, 1, and 1 ds on the surface S. When I do this dot product, oh, let me make sure I've got my crosses here. So this gives me 0, and that's 0. This gives me 1. Cool, that gives me 0. And then this gives me, oh, don't forget that's a negative because its I is in the negative direction. That would have made it more interesting, but it would have been okay. I mean, it wouldn't have been correct, but the integration itself would have been okay. So when I do this dot product, I'm going to get 0. I'm going to get plus 1, positive 1. So plus 1. And then minus 1 ds, which is going to give me the integral of 0 ds, which is equal to 0. So my answer is 0. Now, I really should have, by the way, gave you the limits here for what restricts the x and what restricts the y here. So I'd have to look at what is going to be on the xy plane to determine what's going to restrict the x and the y, not just the y minus z equals 0 plane, but the actual on the xy plane, because I parameterized in terms of x and y to get my limits of integration. take a look at the next example. We're going to use Stokes Theorem to find the circulation following the vector fields around the smooth, simple curve C, where this is given as f. So let me just erase this. Erase this. Erase this. I'm really slow today on my erasing, and my software seems to be a little behind and lagging on what I'm doing. Okay, so I'm going to use Stokes Theorem to find the circulation of the following vector fields around any smooth, simple curve C, where f is given as this vector field. So I know I'm using this circulation of f dotted with a dr, which we know is the surface integral s of the curl of f dotted with the normal ds. Then the curl of f is going to be equal to I, j, k, y, be the next line. Let me erase this. That'll be the next line. Of the partial with respect to x, the partial with respect to y, the partial with respect to z, of y squared is z cubed, 2x. That can't be right. Let me go check. There shouldn't be an extra z there, so let's get rid of that. So 2xyz cubed, and then my last one is 3x y squared z squared. Okay, when I get done with this, I'm going to get something like 6xy z squared minus 6xyz squared in the I direction, which, because they match, is going to give me 0. And then plus or minus in the j direction, 3y squared z squared minus 3y squared z squared in the k direction, which again is going to be 0. And then plus 2yz cubed minus 2yz cubed in the, that was in the j direction, not k. In the j direction, this is in the k direction. Well, look at that, it gives me 0. Well, that tells me that this is going to be 0, because 0 times anything is 0. So that's it for that one. It's not too bad. So on this one, we're going to use the Stokes theorem to compute the curl along the surface area S of f dotted with ds, where f xyz is equal to I plus 3y squared j plus xy squared k, and S is part of the plane y plus z is equal to 2 inside the cylinder of x squared plus y squared, and it is orientated counterclockwise. So once again, we know we have, and there should be an n there. I don't know why I keep dropping that. The surface area of the curl of f dotted with n ds is equal to along the curve f dotted with a dr. All right, so what we need to do is we need to parameterize the curve, and we're looking at the curve, which is the intersection of the plane. So this is the curve. This is my plane, so this is my plane here, where this plane, you can see where it's coming in right here, and this being my cylinder. So my cylinder, so it's like a parabolic shape, sort of. So I need to parameterize that. So we start with the fact that we have this, which if we have that, we know that it's going to be x is going to be r, which is 1 cosine of theta, and y, which is r, which is 1 the sine of theta. We also have this bit of information that says z is equal to 2 minus y. So z in terms of parameterization would be 2 minus the sine of theta. So my r of theta is going to be the cosine of theta, the sine of theta, and 2 minus the sine of theta. That means r prime, these are vectors, r prime of theta is going to give me negative sine theta, cosine theta, 2 minus the cosine of theta. My f of r of theta, not prime, of theta is going to be equal to, I have 1 x times y, so that'll be the cosine of theta, the sine squared of theta, and x multiplied by y squared again, which gives me the cosine of theta, the sine squared of theta. So my theta is going to run between 0 and 2 pi. So then my integration is from 0 to 2 pi of, I'm going to rewrite this as from my curve of f of r t dotted with r of t dt, except for I'm going to be using theta. So from 0 to 2 pi of 1 cosine the sine squared theta, the cosine theta sine squared of theta, dotted with negative sine theta, the cosine of theta, and then 2 minus the cosine of theta, d theta. So I end up with the integration from 0 to 2 pi of negative sine theta, plus the cosine squared theta, the sine squared theta, plus 2 the cosine theta, the sine squared theta, minus the cosine squared theta, the sine squared theta, d theta. Now this is nice. These two cancel themselves out, leaving me the integration from 0 to 2 pi of negative sine theta plus 2 the cosine theta sine squared d theta, which I can rewrite as from 0 to 2 pi of negative sine theta d theta, plus integration from 0 to 2 pi of 2 the cosine theta, the sine squared theta d theta. And again, nice u sub here, let out of control there, let u equal the sine theta, and then you have some nice u substitutions. And when you get done with this, again, this really isn't that bad. My final answer for a whole lot of work is 0. We can interpret the curl as a relationship between curl and circulation as Faraday's law. And it's really important for my electrical engineers out there and the magnetism that creates the curl of electric field. This is also can be applicable to my chemistry majors. Recall if C is a closed curve and F is a vector field denoted by C, then the circulation of F around C is a line integral. If F represents the velocity of the fluid in space and the circulation measures the tendency of the fluid to move in the direction of C. Let F be a continuous vector field. Let D sub R be a small disk with radius R centered at P naught in the figure below. If dr is small enough, then the curl of F with P is approximately the curl around my P naught for all points P in dr because the curl is continuous. We end up with this equation, which means Stokes Theorem implies that the curl of F around P naught dotted with the n with P naught gives me the limit as r goes to 0 of 1 over pi r squared, the integration of the curve around r of F dr. If F is a velocity field of fluid, then F dotted with N is to measure how the fluid rotates about the axis N. The effect of the curl is the largest about the axis at the points in the direction of N, because in this case, the F dotted with N is as large as it possibly can. We want to think of this as like a paddle wheel, and you're going to have the largest number when we have F dotted with N and it's in the direction of N. Faraday's law, we end up with the work, which is equal to the electric field T, the integration of the electric field dotted with a dr along the curve of C. So in other words, we have the curl of the electric field can be interpreted as the negative of the rate of change of the corresponding magnetic field with respect to time. And that's it. That's a full hour of luscious and exciting Stokes theorem, and we'll see you in class.